What if I told you that you could fundamentally hack the biology of a living creature using, well, a 30-cent piece of clay and, like, a basic understanding of high school geometry?
I mean, I'd say you're probably talking about the weird, wild world of aquariums.
You would be right. Welcome to today's deep dive. We are extracting the core insights from a very specific and, frankly, deeply fascinating piece of source material today.
Yeah, it's a post dated April 24, 2026, written by an author named Ang, and the title is deceptively simple. It's just called Notes on Fishkeeping, Part 240.
Which is wild.
It really is.
Yeah.
That title alone tells you are walking into a total masterclass of trial and error. I mean, 239 entries of careful observation preceded this exact document.
It sets a stage of intense methodical experimentation, for sure. So, okay, let's unpack this. Because our mission today zeroes in on a highly specialized aspect of this hobby.
Right.
Ang is meticulously priming a pair of Apistogramma fish for breeding, and the tool of choice for this complex biological process isn't, expensive laboratory hardware.
No, not at all.
It is a repurposed terracotta gardening pot. We are talking about taking the most mundane objects sitting empty in your garage, dropping it in water, and literally using mathematical tweaks to bend nature to your will.
The author is essentially forcing the physical environment to trigger a biological function. It is this perfect intersection of engineering and nature, but within a highly confined space.
Before we get into the actual geometry of this pot, we should probably establish who is actually living inside of it.
Good point.
For anyone listening who might not be deep into the aquarium hobby, what exactly is an apistogramma? Like, we need to know who we are engineering this space for.
Right, so they are remarkable little creatures. Apistogramma are dwarf cichlids. They're primarily native to the Amazon basin down in South America.
Okay.
And we are talking about highly intelligent fish that max out at maybe 2 or 3 inches long.
Very small.
Very small. And in the wild, they live in these dense, slow-moving tributaries that are absolutely littered with fallen leaves, submerged tree roots, just all sorts of natural organic debris.
So they're used to a very cluttered, highly complex environment. I mean, they aren't just swimming in open, empty water.
Oh, far from it. And crucially for our discussion, they are notorious cave breeders.
Ah, okay.
In the Amazon riverbed, a female apistogramma will meticulously scour the environment, looking for the absolute perfect crevice.
Just hunting for the right real estate.
Exactly. She might choose a spot under a sunken log or maybe inside a hollowed-out seed pod. She is looking for a hyper-specific microhabitat to lay her eggs.
Which brings us back to the humble terracotta pot. Because in a glass tank in someone's living room, there is no infinite Amazon riverbed to explore.
No, there's not.
There's literally just what Ang puts in the water.
And the aquarist carries an immense burden here, In captivity, every single architectural choice has massive consequences.
Because it has to replace the infinite variables of an entire natural ecosystem.
Right. The texture of the clay, the size of the opening, the exact angle of inclination these artificial substitutes have to do the heavy lifting of a complex natural world.
Or else it just fails.
Yep. If the environment isn't properly calibrated, the biological processes simply will not initiate. Full stop.
So Ang provides this terracotta pot to serve as that artificial cave. But the specific trick being tested, the hack we mentioned earlier, is physically tilting the cave.
Yeah, that's the key.
Ang is positioning the pot so the opening sits significantly lower than the back of the pot.
It's a very deliberate alteration of the space.
Yeah.
You are creating an artificial grade, a slope that simply doesn't naturally exist in the geometry of a standard flat-bottomed pot.
Right, but knowing the physical setup is one thing, but it begs the question, why does a fish care about a slanted floor?
It's a great question.
Let's look at the first reason this tilt actually matters. Ang notes that the low entrance and the elevated back allow the female to stay tucked away at the very top of the cave.
Mm-hmm.
From that specific position, she gets a clear view of the outside while remaining completely hidden in the shadows.
What's fascinating here is how this touches on the fundamental concept of psychological security in animals.
Right.
We tend to think of breeding as a purely mechanical or physical event. But psychological security, profound threat reduction, is a mandatory prerequisite for reproduction.
Especially for a tiny prey species like a dwarf suchlid.
Exactly.
Here's where it gets really interesting. I was trying to picture this vantage point, and the best way to visualize it for you listening right now is to imagine sitting in a pitch-black movie theater, looking straight at a brightly lit screen.
Oh, that's a great way to put it.
Or maybe like sitting in your car at night with the interior lights off, watching a lit up street. You can see every single detail of the illuminated space in front of you, but anyone standing out in that light cannot see you sitting in the dark.
The shadow acts as an absolute shield. Because in the wild, breeding is arguably the most vulnerable state an animal can be in.
Totally exposed.
Yeah. The female is stationary, she is expending massive amounts of caloric energy, and eventually she will be guarding immobile, completely defenseless offspring.
So if she feels even slightly exposed.
Her biology will shut the entire process down.
Wow. Just like that.
Just like that. If she feels a larger predator could ambush her, or even if her line of sight to the entrance is obstructed, her brain floods with cortisol.
The stress hormone.
Right. And those stress hormones will actively override her reproductive drive. Being hidden in those elevated shadows isn't just a comfort preference, it is a biological requirement.
So the environment is actively dictating her internal chemistry.
Precisely. By angling the pot, Aang has engineered a space where ambient room light or the tank light simply cannot penetrate to the deepest elevated part of the structure.
It creates a pitch black sanctuary.
Exactly. But because the entrance is sloped downward, her line of sight effortlessly reaches the lit environment outside. She monitors the perimeter without ever exposing her position.
Okay, so we have this female securely positioned at the elevated back of her clay fortress. She's safe, her cortisol levels are down, the environment is telling her body it is safe to proceed.
All systems go.
But if she is tucked all the way in the back, high up in the dark, how does the actual breeding happen? Like the male has to interact with her somehow.
And this shifts the conversation from the psychology of defense to the literal physics of reproduction.
Right.
Because the male doesn't just swim up next to her in this specific dynamic.
Yeah, the notes detail that the male actually releases his milt at the cave's entrance. For those who might not know, milt is essentially the fish equivalent of seminal fluid.
Right.
So he is positioned down at the lower entrance, and she is up in the back. And Aang points out that the upward tilt of the cave naturally helps guide that milt toward the back and the ceiling of the cave, leading to a much higher fertilization rate.
Which is just brilliant.
So what does this all mean? I have to challenge this concept a little bit.
Okay, go for it.
We are talking about an underwater environment where fish are actively swimming. They are darting around, moving their fins, creating their own chaotic microcurrents in the tank.
Sure, water is always moving.
Right. So how does a slight tilt in a stationary piece of clay overpower the sheer chaos of the water around it to act like a funnel for genetic material? It sounds almost too perfectly engineered to be real.
It is a very fierce skepticism, honestly. To understand how a stationary pot wins that battle against chaotic water currents, you have to look at the specific physics of water
Okay.
and the relative buoyancy of the biological material involved. Milt is not the exact same density as the surrounding water.
So it doesn't just instantly dissolve or sink like a rock to the floor.
No, it has a specific viscosity and a slight buoyancy to it. When the male releases the milt at the lower entrance, it actually tends to rise slightly and drift.
Ah, I see.
If the cave ceiling were perfectly level, that material would either hit the flat ceiling and disperse chaotically, or those erratic fin movements you mentioned would easily wash it back out the front door.
Into the open tank where it becomes entirely useless.
Exactly, because there is no structural mechanism capturing it.
But when you introduce an upward tilt to the ceiling, you fundamentally change the fluid dynamics.
You do. The ceiling ceases to be just a roof and becomes a guiding track.
It makes me think of holding a spoon at an angle under a running faucet. Oh. When the water hits the curve of the spoon, it doesn't just splash randomly in every direction. It actually hugs the surface and glides right along the upward curve.
That is a brilliant analogy. The curved, tilted ceiling of the terracotta pot performs the exact same function.
That is wild.
It captures the natural upward drift of the milt, utilizes the microcurrents created by the fish themselves, and physically channels that material up the slope.
Guiding it right to the target.
It guides it directly to where the female and the eggs are located at the elevated back.
So the cave is actively concentrating the genetic material.
Without that specific geometric angle, the dispersion would be wildly inefficient. The physical environment is acting as an active, crucial participant in the fertilization process.
The environment is a tool being used by the fish, but calibrated by the human.
Exactly.
But knowing that fluid dynamics can carry this material reveals a serious flaw in Aang's original setup, because the notes reveal that the current tilt isn't actually getting the job done.
And this is the scientific method in real time. Observation leading to necessary refinement.
Right. Aang looks at this pot in the tank and realizes the angle is currently sitting at about 10 degrees. And Aang determines this simply isn't enough to work.
Yeah, 10 degrees is pretty flat.
The microcurrents are weak, the water is heavy, and a tiny 10-degree tilt just isn't fighting gravity or the ambient tank flow enough to move that genetic material upward efficiently.
A 10-degree incline barely offers a hydrodynamic advantage in a dense medium like water.
The notes specifically say they need to be much more aggressive with the angle. Aang proposes pushing it closer to 30 or 45 degrees for the funnel effect and the shadow effect to be truly optimized.
Which is a massive jump.
Right. Now, when I read that, I started wondering about the biological consequences of an angle that extreme.
How so?
Well, a 45-degree tilt is practically a slide. Wouldn't the eggs just roll right out of the pot? Like, how do they even adhere to a surface that is that steep?
If we connect this to the bigger picture, this highlights the paradox of this kind of environmental hacking. You are constantly pushing the boundaries of what the fish can physically navigate in order to maximize a specific mechanical advantage.
Right. It's a balancing act.
But to address your concern about the eggs rolling away, Apistogramma eggs are highly adhesive.
Oh, really?
Yeah, in the wild, they regularly spawn on the undersides of sunken leaves or vertical pieces of driftwood.
So they're essentially glued in place by biology.
These secrete a natural adhesive. So the steepness isn't a problem for the eggs to anchor at all. But the steepness is the absolute solution for the fluid dynamics.
It solves the flow issue.
Aang isn't guessing here. They are observing the physical realities of the 10-degree setup and finding the physics lacking.
The milt isn't gliding up the spoon, so to speak. It's getting lost.
Exactly. The slope is too gentle, allowing too much dispersion. And simultaneously, that 10-degree angle probably doesn't drop the back of the cave deep enough into shadow to fully eliminate the female's cortisol response.
So she might still feel partially exposed.
Which means her stress is lingering and the fertilization is inefficient. It's a lose-lose.
But by aggressively increasing the geometry to 30 or 45 degrees, Aang is forcing the environment to work infinitely harder.
Yep. The steepness creates a definitive, harsh shadow line for ultimate security. It creates a pronounced, inescapable funnel for the fluid dynamics.
It is a precise mathematical adjustment required to force a biological success.
It takes something that seems so passive, just watching fish in a tank, and reveals it to be this highly active, deeply analytical relationship between space and biology.
Let's briefly recap the journey we've just taken through Aang's notes for everyone listening.
Sounds good.
We started with an everyday, unremarkable object, a terracotta garden pot. But we learned that when this pot is angled at exactly 30 to 45 degrees, it completely transforms.
It ceases to be a simple piece of clay and becomes a highly engineered habitat.
It becomes an optimized, shadowy fortress. An architecture of defense that gives the female a perfect, secure vantage point, effectively shutting down her stress hormones.
Mm-hmm.
And simultaneously, that aggressive, steep angle mathematically increases the fertilization rates by physically funneling the male's milt right up the ceiling to the back of the cave, utilizing the natural buoyancy and fluid dynamics of the water.
It perfectly aligns the psychological needs of the animal with the mechanical efficiency of the environment.
And the real takeaway here, the thing that I think makes this so compelling, is the reminder that in nature and definitely in captivity, the tiniest physical adjustments matter immensely.
They really do.
We are talking about just a few degrees of elevation. The difference between a 10-degree tilt and a 45-degree tilt is literally the difference between biological failure and biological success. The geometry dictates the life cycle.
It is a profound testament to how deeply connected living organisms are to the spatial realities of their immediate surroundings.
Yeah.
The architecture around us shapes our outcomes.
The architecture shapes the outcome. And that leaves me with a thought that I've not been able to shake since reading this, and it's something I want you to mull over on your own as you go about your day.
Yeah.
We've just spent this entire time talking about how a mere 30-degree tilt in a piece of fired clay can completely transform the success rate of a complex biological process for a tiny fish.
It changes their behavior, their security, their future.
So it makes you wonder what invisible angles or structural tilts exist in our own daily human environments.
Ooh, this raises an important question about how we construct our own lives.
Right. Think about your office. Think about the layout of your home or the geometry of your city streets.
Yeah.
What physical structures are subtly dictating your behaviors, your stress levels, your successes, or your failures without you even realizing it? Are you sitting at a 10-degree disadvantage right now, struggling against the current, when a simple environmental shift could change everything? Think about it.